Okay, so maybe we can get to the next slide. And hello, everyone. Welcome to the People GSoC kickoff meeting. Today, we are going to have our GSoC contributors presenting their project proposals. And we have a pretty tight schedule. So if you want to learn more about People GSoC program itself, you can check our GitHub repo. And if you want to participate in further discussions, we also have a Zulip channel for that. Now back to the meeting. Before the project proposals, we are also lucky to have Professor Nate Foster to give us an introduction talk. So without further ado, let's welcome Nate.
Great. Nice to be here. Thanks for inviting me. Denise, can you move forward a couple of clicks? So I want to talk a little bit about P4's future. And I'll just start with a little bit of context. You might know that P4 emerged and was kind of co-developed with the first generation of fully programmable switching chips. So in particular, the Tofino chips that Barefoot and Intel produced. And a couple of years ago, Intel announced that for business reasons, they were ending development and then production of Tofino switches. Next chart. And a lot of people thought that that this would sort of end P4, that P4 was sort of hopelessly entangled with Tofino, and therefore the language had no future. And when this happened, I heard a lot of cynical views from people in the community and even a little bit in the press. And you heard things like, well, programmability never really made sense anyways. Next chart. Or open networking, which is this larger movement that P4 is part of, the idea that we should sort of break open the traditional sort of vendor-controlled version of the network ecosystem and expose interfaces and languages and tools to the network owners. So there's also a sense that maybe that was in decline. Next chart. And then for P4, there were people saying, well, if there's no target that supports P4, the language will eventually die. Next chart. So I never believed this cynical view. I just wanted to start with that because I think you may hear it, and it's helpful to know that it's out there. But I think that actually, again, Tofino was canceled for purely business reasons, and in fact, this trend towards network programmability, which has been going on really for decades and quite intensely over the last, say, 15 years, I think it's an inevitable trend. And the reason is that, well, if you look inside of what vendors have been building, whether it's switches or NICs, they've long known how to build network devices that have various forms of programmability. They usually didn't expose it to customers because there wasn't an ecosystem and there wasn't a conversation about having open and programmable network devices. But I think there's good reason to believe that that may be coming. And maybe one way you could see this is that, Moore's law, which has been the thing that spurred the growth of the whole computing industry, well, it's been powering the growth of networks as well, right? Every generation of a NIC or a switching chip, things get faster and faster, more bandwidth and more capacity. But now there's sort of a mismatch because Moore's law has really ended on CPUs. It's still going strong in the network fabric, but due to this mismatch, the need for some form of in-network processing, whether it's offloading, different functions to the network because there's capabilities that the network devices can do more efficiently, or whether it's just the ability to observe and debug what's going on. If you're doing a building an ML fabric for training or inference, and you've got failures or you've got weird bottlenecks, understanding where those things are requires some ability to program the fabric and debug. And so, I think that for fundamental reasons, we're going to need the ability to do a lot of the things that the P4 community has been working on for the past 15 years. And it's unlikely that there will be sort of just a few one-size-fits-all solutions. I think vendors and network owners are going to have different needs and want to differentiate. And the only way to support kind of all the forms of rich customization that I believe will be necessary is to have support for programmability. So as I'll show you in the next few slides, I believe P4 actually has a kind of very promising future. And the work we've been doing in the P4 consortium over the last couple of years has really shown this. P4 is being used in some cases quietly and in some cases publicly by multiple hardware vendors. So there are credible P4 targets today. And there's also growing use of the language just in pure software, whether it's for specification and validation or for doing packet processing in software in ways that can maybe be amenable to offloading to hardware in the future. Next chart. Okay, so a little bit about who we are. The P4 consortium used to be an independent nonprofit. Then we were part of something called the Open Networking Foundation. And since early 2024, we've been part of the Linux Foundation. This has been a really positive development. We've really grown up in terms of our organization and our financial structure and how we run things. Maybe one of the more positive developments is we've actually recruited a set of diverse members, both industry members who provide a lot of the funding and guidance for where the consortium is going, as well as lots of universities who have signed on to be a part of our group. If you're here on the call and are not part of an organization that's a member of P4, happy to talk to you about what it means to join and how you can get involved in our activities. Even if you don't become a member, whether it's through the working groups or joining calls like this, we're very eager to grow the community and to have your help in helping P4 continue to evolve and mature, and of course also shape its future direction. Next chart. Okay, so I just thought I'd tell you a little bit just to give some concrete examples of how P4 is being used. So again, 2 years ago, there was really no switching target that was publicly announced that supported P4. And today there's at least two. So Excite Labs is a startup that's been building a fully programmable switching chip. They actually support a low-level ISA, which is quite flexible. And that ISA can be used to implement languages like P4. And they're a member of our consortium and very eager to harness all the momentum behind P4, and they have a very credible hardware target for realizing programmable functionality. And then also this year, Cisco has publicly announced that their Silicon One switching chip supports P4 programmability. So that's another, from a very traditional, prominent vendor. There's the ability to write P4 code for a high-speed switching chip. Next chart. Another area where there's a lot of use of P4, so pretty much all of the leading NIC vendors have announced P4 support on different varieties of NICs, primarily smart NICs, but also some so-called foundational NICs. So AMD, Intel, and NVIDIA. And I think here one of the interesting things is that P4 really was co-designed with a switching chip in mind, but NICs have more capabilities, and so the conversation about how to use P4 on NICs is helping drive evolution of the language. So features for encoding things like transport protocols or cryptography, how you interface with the memories and interconnects that get you back to the main host. These are all things that, of course, you can model them in P4 just as we call them externs, but it's, I think, more interesting and useful to actually evolve the language to allow these things to be expressed natively. Next chart. P4 is also, as I mentioned, being used in software. So there's targets like P4DPDK. There's a group of kernel hackers that have built a path for taking P4 code and running it in the Linux kernel. This is, I think, interesting and cool, and it's also led to a noticeable uptick in contributions to the open source compiler and simulators. Next chart. And then lastly, one of the surprising uses to me is that P4 has actually been useful as a specification language. So some folks at Google, including some people on the call, have been using P4 to model and validate their data center switches. So they're not actually programming the devices with P4. They're just writing down these models that they then use to drive all kinds of testing and other validation. And they have a paper at SIGCOMM 22 that describes this. There's also some use in the Dash project, which is part of Sonic, using P4 to get an executable specification for reference pipelines. And there's other tools like P4 TestGen, which give you the ability to automatically generate comprehensive tests for P4 programs. Next chart. So I think, we continue to be in a period of rapid transition, which is exciting. I'm very optimistic that network programmability is here to stay. And I think P4 is an excellent vehicle for exploring these ideas for a diverse set of data planes. And I just want to close by saying, P4 is, the community is kind of vast. So it includes, of course, academics, companies, but also just, grassroots contributors through the kind of traditional mode of open source. And so we're incredibly grateful for all the work that you'll do this summer through the Google Summer of Code These are taking on projects that are strategic and important for us or develop new capabilities. And we literally could not do it without your efforts. So we're really grateful that you're spending your time with us this summer and looking forward to seeing what you produce. All right, stop there.
Yeah, thanks, Nate. So it seems Andy is saying there are some slides issues. Okay, so
if everyone else sees them, that's fine.
Okay, so maybe for next speaker, you can share from your side. So for the next talk, let's welcome Shi.
Hello.
Yeah, so could you share your slides?
Yeah, sure. Let me bring them on.
Thanks.
Okay, can everyone see my screen?
Yes.
Okay, cool. So my name is Haoxi, and I'm currently a master's student major in computer science at New York University. And I'm interested in distributed systems, networks, and compilers. And currently I'm conducting research on BFT problems and some P4 enhancements. Okay, before dive deep into my project for the summer, I need to clarify a few keywords, and please interrupt me if you have any questions. So, what is BMV2? BMV2 stands for Behavior Model Version 2. It's basically a software simulator for P4 data plane and control plane, and it offers various toolkits and interfaces for developers to develop their own architectures or models. For instance, it currently supports V1 model PSA and PNA. And what do I mean by all possible outputs? So P4 supports various constructs that help developers to develop multi-pass behaviors like equal cost multi-pass routing strategies. And here, all possible outputs just refer to the all possible outcomes that derived from such multi-pass constructs. Cool. Here is an example for the end result of my project. So in ECMP, equal cost multipass routing strategy, say we have a selection strategy called round robin. Basically, it means that, for instance, we have 3 egress ports, and for a single packet, it will be routed to one of them, and for the next packet, it will be routed to the next egress ports. Basically a round-robin fashion. Traditionally, one header state would be obtained, like the green one, from such selection. But our goal is to obtain all possible header states that gets processed by the constructs, like the figure on the right-hand side, where we have all possible 3 header states. But why this matter, right? So as far as I can see, there are 2 things that makes it important. So first one is diff testing. So we want to compare the result of deployed P4 switch. Like in our model, we simulate the behavior of our P4 programs, and we would like to see what is the all possible output and compare with the deployed switch results to see if the latter one is the subset of the former one. And second, it's good for deterministic behavior and better test coverage, like constructing proper inputs to explore all possible code paths could be burdensome for developers. Like in my previous example, where we have a round-robin fashion equal cost multipass routing strategy, but in most of the time, it's actually a hashing selection strategy. So it is weird to see that you want to construct an input that maps to a hash result that can help you to go through a specific code path in the multi-pass constructs. So with this feature, we would hope that fewer tests could be built. But there are challenges. Like essentially, we want to replicate packet headers and continue them into the whole processing pipeline. But how do we do this, right? And the second issue is that we need to preserve the switch and program states. Like, for instance, we have counters, which count the number of packets that goes through the pipeline, for instance. But if we replicate the packet header, packet states, then we would count redundantly. It's probably not quite correct in this sense. So here are our approaches. So in order to continue the header states in our pipeline, we basically record the next control flow node or table after the selected action for each replicated headers, and then continue from the node one header by one header. I think it's a clean way to solve this issue. And for the program and switch state issue, we propose a snapshot mechanism to capture the current state of the switch or the program before we replicate the header states, and to make sure that the resulting state is desirable. And finally, the deliverable for our project for this summer will be an interface or a mode or pragma that replicates header states for all possible selections and obtains the resulting states. And that's it for my proposal. And please let me know if you have any questions.
I have one, and I don't want to derail your project, but it just occurred to me that another possible way to achieve this goal might be no modifications to BMV2, but maybe a modification to something, a tool like P4 test gen that identifies, you give it one packet that hits the action selector and it tries to identify new input, similar input packets that take the same initial path but diverge at that point.
Oh, so you are referring to concolic testing, but I think it works. But the issue is that you still have to construct something, and you don't know if the input would be actually aiming for the particular path that you are trying to permutate on. And the project, my project is trying to solve the issue that, for instance, in profile selector, there are members within the group to be selected on. And our target is to simply permutate all the possible action members within that group. And constructing input does not necessarily help this scenario. For instance, in the round robin example that I have, there is no way you can construct a specific input or a concolic test that can target to a specific member in that case.
Thanks.
Any other questions for Xi? Okay, if there are no further questions, let's move on to the next project proposal from Vineet.
Yeah, hi. Just let me share my screen. Now, am I audible? And can you share my screen?
Yes, we can see your screen and we can hear you.
Yeah. So, hi everyone. Myself Vineet Kaur, and my project is P4 Simulator, enabling P4 simulations in NS3. So let me walk you through a detailed overview of my project. First of all, a little bit introduction of myself. I am an undergrad student at Indian Institute of Technology, Roorkee. I'm interested in Web3 system design and software development, and I love to play video games. And here are all the links through which you can connect with me. So before starting, let me give you an introduction about P4 Simulator, short form P4 Sim. So P4Sim is a high-performance P4-driven simulation framework built on BMV2 and NS4, and it is seamlessly integrated with NS3. The key strengths of P4 simulator includes the efficient switch modeling, uh, implementing the P4 architectures. Basically, it implements the three architectures, which are the V1 model, the PSA, and the PNA model. It enables protocol independence and it is seamlessly integrated with NS3, which helps to create simulations using the P4 devices. And here you can find it is open source, and you can find here I provided the link for the repository. So here is the structure of P4 simulator. This figure particularly implements the PSA architecture. This So you can find all the things in here, but the thing which is lacking in here is the current limitations of P4 simulator, which is the control plane. The current implementation of P4 simulator seamlessly integrates NS3, but it lacks the control plane implementation, which is basically a major feature for P4 switches. So my GSoC project aims to solve this gap. Uh, aims to solve this gap. So here are my clear-cut goals for this project. First, I will be implementing a full working control plane for the P4 simulator. Then I will be adding some data collection and tracing mechanisms so that you can view the performance and analyze the switches performance in the simulation. And then I'll be writing some testing and example scenarios for the project and completing the documentation so that further enhancements can be made upon this project. So here is a technical approach to the project. So the way NS3 works is basically it has some abstractions like the node abstraction, which relates to the actual host in the real world. It has application like the UDP application, TCP application, which runs on the host or basically node, and various 3 to 5 abstractions through which you can build a network and test those framework on the NS3 simulator. So my similar to this, the P4 simulator also has some two classes, the P4 SwitchNet device and the P4 switch core. The P4 switch core helps to implement the V1 model, the PSA and the other PNA model, and it helps to packet process forwarding and broadcasting the switches. And the P4 SwitchNet device is similar to the net device class in NS3. Basically, P4 SwitchNet device helps you to create switches in the NS3 and install those switches in the host computers. So my job will be to implement the controller module, controller module in this P4 simulator project. So here you can see this dashed path, which I have to implement. The main task is to implement the controller and then add some tracing mechanisms to get the performance of the switches. So here is a brief timeline of my project. On 2nd June, I have started coding of the project. And by the midterm evaluation, I plan to deliver a full working control plane so that we can have a working control plane set up and test other networks on using the P4 switches. And by September 1, I have a plan to deliver the final project, writing the tests and the documentation and submitting the final code. So here are some benefits to the community which this project will have, like the education utility. It will help the researchers and students to explore the P4 switches more. It will help debugging the P4 switches more, basically using the simulations framework, and offer a broader support for P4 ecosystem as well. So thank you for your time. That's it from my side, and I'm open to questions.
So I have a question regarding like NS3, this simulator framework or something in general, like what is the typical use case of the NS3 simulator as compared to other simulators?
So what NS3 has is NS3 works on virtual time. So what happens is basically when an event happens, the time starts in the NS3 module. And NS3, basically NS3 provides various channels, various like the Wi-Fi channel, the Ethernet switch, the CSMA channel, through which you can build your whole computer network and test those networks in the actual real world simulation kind of thing.
I see. So guys, so NS3 is like a network-wide simulation, like involves multiple switches, and this work is kind of
Yeah,
integrating
I
the
mean,
people. Yeah,
yeah. Like if you want to test a simulation network, like if you want to design a network for a building, so that you cannot test that in the production. So first of all, you have to test somewhere else, so that you can analyze the performance. So there you can use NS3, like building the whole the topology, then adding switches, adding the real life test cases like error handling and all these cases, so that you can get the actual performance of the network. So you can design and implement those in the real world of it.
I see. I also wonder, like, how is BMV2 integrated into this? Is that is used as a library and running as a sub-processor?
Oh, so basically, what happens is the code which is written in the B1, B2, like the BM simulator, the BM simulator, and all the other things which are implemented in the BM V2, uh, we have used that code and just with some slight modifications, we have implemented the classes in the P4 simulator. So you get to basically you get two classes, the PA4 SwitchNet device and P4 switch core model. So P4 SwitchNet device implements the network device, net device, it relates to the net device class in the NS3, which is basically used to install the network devices. Like the P4, you can use the P4 SwitchNet device class to install your P4 switch onto your host machine. So there the we have used the code from BMP to use in the P4 simulator.
Okay, got it. Thank you. And are there any questions for Vinit? Okay, if no further questions, let's move on to the next talk from Xiaomin.
Hi, sorry. Could you guys hear me?
Yes.
Yes, we can hear you.
And could you see my slides?
Yes, we can see your slides.
Okay, perfect. Hi, everyone. So my name is Xiaomin Liu. I'm a Queens, New York City native. I'm also pursuing a bachelor's degree in computer science at NYU. Um, my interests are more in the compilers and programming languages side. And I'll be interning at Google this fall working on their SmartNICs. So my GSoC proposal is working on what's called MLIR. MLIR is a sub-project of LLVM. It stands for Multi-Level Intermediate Representation. And as the name suggests, it's a compiler framework for representing code at various levels of abstractions using custom IR called dialects. So it's essentially a way to construct IRs and the transformations between them. So why are we considering using MLIR? So P4C right now currently suffers from performance issues that are rooted in its design. So so a couple things are, so there's an excessive memory usage. So for example, the def use pass, which stands for define use, it's a type of data flow analysis. That pass can consume almost 16 gigabytes. Another issue is that P4C is built on using immutable IR, but it also modifies its IR, which means that it leads to a lot of copying of nodes and even whole programs. And it also has long compile times compared to other compilers, even though P4 is a relatively simple language. So this is a diagram of what we'd like to do for the project. So at the very top on with the purple, you see the current P4C. So the idea is we'd like to hook our P4 MLIR project right before any sort of like front end or mid end passes, or like a lot of their optimization passes, and we just get the P4 IR right after it's parsed and there is some type inference on it. We build something called P4 MLIR translate, which translates this P4 IR into our P4 HIR, which is our P4 high level IR dialect. And the goal here is before, like I should have drawn something here, sorry about that. But before doing all the arrows to the backend, we'd like to do essentially do something similar to what P4C does, and do a lot of the front end and mid end passes. Yeah, and then so what is the sort of progress that P4 MLIR is at today? So right now there's it makes control/data flow explicit while preserving high level P4 semantics. So most basic statements and translations from the P4 front-end IR are already implemented, and we have already started implementing a couple, like 1 or 2 existing P4 front-end/mid-end passes. So this is like a very simple program, and this is what it would look like in P4 HIR. Here you can see that there's a function. It takes in its argument, and we annotate the argument with both the direction and the parameter name. We also, and here are some like MLIR operations. Yeah, so the goal by the midpoint is, so right now there are about 57 front-end and mid-end passes in the entire P4C repo. Some front-end passes are required to perform type inference, and other passes can be skipped since they're not really needed. And then and the issue here is that every pass in P4C needs to copy the entire program, even on like small changes. So the goal here is to try to reach functional parity with existing P4C front-end and mid-end passes, but within the MLIR framework. And sort of the deliverables by the end are 1, to address core performance issues, so improve data structure usage and improve some of the slightly suboptimal implementations of some of these passes. And what the next thing is to design a replacement for the USDEF analysis pass with MLIR using the MLIR data flow analysis. And then another goal is basically to, like long-term goal is to lay a groundwork for backend extensibility by lowering towards LLVM IR. So from my understanding, at least, is that right now, to, for example, compile down to BPF, we take P4 source, P4C emits some C as an intermediate step, and then we run Clang/LLVM on that C source to generate that. And the idea is that this is not like a direct representation. So there are some things in P4 that you can't exactly represent in C. So there's like information loss as you go, as you lower the program. And any questions? And I might have answers, maybe.
It seems surprising to me that there are things in P4 that you can't express in C. I would have expected this arrow to sort of go in the opposite direction. Maybe you just mean that it is very hard to express it in C and not worth the time? Or you think this is fundamentally impossible? What's the...
I believe it is like very difficult. I'm not really sure, to be honest. Maybe
Maybe an example would be a P4 ternary table, which would require some library to be written in C to emulate it. Maybe
yeah, maybe are there examples that you have in mind, Shaman? That would be useful.
Sorry, I don't really have an example. Sorry about that. I might.
I would probably say, yeah, I would probably say that, well, saying that, well,
it is impossible to represent is probably wrong motivation. But what here looks, well, not right is, well, the BPF backend currently is essentially, well, template interpolating thing, right? So it just speeds the like text substitute, like a program like substituting things as text without, and then this thing got like parsed again and passed through the entire like client compilation pipeline, for example, through the LLVM IR and so on. And the understanding is that we can like lay the ground to put the shortcut here, like because via MLIR we even have the two possibilities here. One is that we can skip the C part entirely, emitting directly LLVM IR plus some well additional boilerplate here and there, like skipping the entire like requirement for the additional like C compile at all. Or alternatively, we can do better. So instead of text interpolation, we can use the existing emit C dialect that is able to like represent the C constructs, but in much more structured way. So yeah, that is it.
That makes sense. Thanks, Anton.
Are there any other questions for Xiaomi?
Is it, I don't know sorry, I haven't followed the P4 MLI project closely yet, but is the goal to re-implement P4C front emit in passes on that IR, or is there, I thought part of it was you could maybe take advantage of some LLVM backend kind of thing and not have to re-implement all that stuff and get other optimizations for free.
Yeah. So the goal here is not just like blindly re-implement. Maybe I shouldn't have phrased it like that, but it's more both. It is both also like analyzing if there are any like front end / mid end passes that are not necessarily needed because they are already like given. They're already like sort of givens in MLIR. So yeah, you're exactly right.
Yeah, let me give you an example. So we already get the inliner like up and running, and the amount of work required for that was just essentially running 10 lines of code of like hooks just to represent the underlying semantics to high level inliner implementation, and that I think is a great example here.
Yeah, thanks, Xiaomi and Anton, for the explanation. So I think it's time to move on to the next project proposal, and it's from Advay.
Yeah, you guys see my screen?
Yes, we can see your screen. Yeah.
Okay, sounds good. So hello everybody, I am Advay Singh. I'm an undergraduate at the University of Michigan studying computer science, and this is my first time contributing to an open source project, especially one of this scale. So in a lot of data center environments, the final machines tend to have a lot of virtual machines, and there needs to be a way of routing to these virtual machines. So there tends to be a virtual switch in software. This virtual switch has its own pipeline, sort of like an open flow pipeline usually, which routes the virtual machines, and this tends to be the final hop. However, this virtual switch is CPU intensive and slow because it's completely in software and it's not like the line rate in ASICs. So this new idea of single root IO virtualization has been developed where you offload the cache pipelines or determine which flows determined in where they be routed in the pipelines directly to the SmartNIC itself, which can then route to the virtual machines. However, there's still a problem with this. These accelerators don't have nearly as much space as a normal CPU. And due to that, there's a lot of hardware cache misses, especially in the case when there's less traffic locality in the network. So due to this idea, something called GigaFlow has been developed, which is a much higher accuracy hardware cache. So GigaFlow leverages pipeline locality, which is the pipeline of the locality of the traversal within the pipeline, and also rules-based reusability. And the key idea of GigaFlow is to break the OpenFlow pipeline traversals into multiple sub-traversals, which the flows can share. So just to kind of look at what the architecture looks like, you can see at the top right of the image how the initial pipeline was broken down into multiple sub-traversals using a partitioning scheme. These sub-traversals are then used to create and install longest traversal matching rules into P4 tables. And these P4 tables are called GigaFlow tables. And together this makes the GigaFlow cache. So what does the GigaFlow cache actually look like? Well, the GigaFlow cache is a pipeline of these P4 tables full of longest traversal matching rules. So here you can see the code for a GigaFlow table or a general GigaFlow table. So a lot of the fields are ternary and are pretty standard fields that flows would match on in the case of OpenFlow. However, there is one exact match field, which is the table tag. The table tag here is to ensure that the sub-traversal, or as this packet is traversing through the GigaFlow tables, it matches the pipeline that it would have traversed through in software exactly. So this is also used to determine priorities. And by that, I mean the sub-traversal or the GigaFlow table that takes up the longest sub-traversal in the original software pipeline is the one that this packet should go through in the case when it matches on multiple flow rules. So this ensures correctness. Another thing to note is that there is some pretty standard actions here, and there can be more actions introduced, but some of the standard ones are forward drop and in inserting this table tag. Then, as I previously mentioned, the GigaFlow cache itself is just a pipeline of these GigaFlow tables full of these longest traversal matching rules. So what are the challenges right now? Well, currently GigaFlow is only a software emulation. The proof of concept is there. We know that it has much higher accuracy than the traditional hardware offload caches. However, there is no current hardware supported. So my goal in the summer is to create the offload for the Alveo U250 accelerator, AMD Alveo U250 accelerator board, and more importantly, through that, create a template for hardware offload of GigaFlow caches on other P4 enabled accelerators. So to go more in depth on what my actual plan for the summer is, firstly, I'll be writing all the P4. So this P4 has all the GigaFlow tables, the pipeline that I mentioned earlier. And then using the AMD P4 SDNet toolchain, I'll be creating a bitstream, which I'll install into the Net FPGA shell, an open source Xilinx shell, which allows accelerators to act like network devices. So you can see how there's multiple RX and TX queues here. Essentially, these are physical ports and QDMA ports to virtual machines. And you can see how the GigaFlow pipeline is also in the center there to determine the actual routing logic. Then, using the AMD Vivado design suite, I'll upload this bitstream into the AMD Alveo card. And from there, I still need a way to install the rules once this bitstream has been generated and installed into, or the GigaFlow tables have been installed into the accelerator. The way to do that is to write the SDNet driver, the AMD SDNet driver, to be able to install rules onto these tables. But now we need to know when to install these rules. This is done in upcalls in Open vSwitch when the hardware misses. For that, I'll actually have to switch or add modifications to Open vSwitch to also generate this longest sub-traversal scheme code for that. And then together, once I have that, the Open vSwitch have been modified and the SDNet driver is there, I can install these P4 rules into the GigaFlow table. So the current infrastructure that I'm working with looks somewhat like this. So everything in green here is a physical machine. There's a collector machine, an Open vSwitch machine, and a TGen machine. So the Open vSwitch machine is just to represent any other data center machine. And the collector installs OpenFlow rules to this machine so that it can create its own software pipeline. It also installs mock traffic to the TGen. And then it collects logs from both of these as part of the experiment just to see the actual hardware offload, having cache hits, etc. The TGen just has a standard NIC, which sends and receives TX and RX traffic. And then there's also a Gigaflow backend accelerator card with the OVS machine. This is the one where it actually installs these longest traversal matching rules and also handles the up call misses I mentioned earlier. So what's the value in this project? Well, Open vSwitch is the most popular virtual switch in the world. So many companies use it and it's used in data centers across the world. And all its improvements have been incremental. So just to kind of look at how originally this is a standard design for Open vSwitch. There's a user space and a kernel space, and the pipelines tends to be in user space. But realizing that the user space was much slower than the kernel space, people installed microflow kernel caches, which are exact match caches into the kernel so that things can just be routed directly from the kernel. And then realizing that this was too exact and things like the IP hop count was something that was not allowing packets that belong to the same flow to be classified as part of the same flow. There was now megaflow kernel caches developed, which were more broad. From there, data plane development kit, which basically just allowed the user space pipeline to communicate with the drivers themselves without having to go through the kernel and copying there. And then there was also the AFXDP because people wanted to leverage the existing kernel infrastructure rather than having to write completely new DPDK full mode drivers. And then single root IO virtualization more recently. But now it's time for Gigaflow. So for the future work is to actually use this created template of the AMD Alveo U250 offload to add more P4 enabled devices to the backend of the OVS with Gigaflow. So these are some of the most popular ones that could be potential candidates. AMD Pensado and NVIDIA Bluefield are some of the DPUs. And yeah, so this is gonna have to be my question slide. Thank you.
Any question for Adley?
No, seems like super cool work. Nice.
Yeah, thank you, Adley. So then let's move on to our last talk for today from Sankau.
Hello everyone, I hope my screen is visible. All right, so myself Sankalp Jha, and my project is split decision tree, scaling stateful decision tree algorithms in P4. So yeah, this is a bit about me. I'm a Bachelor's of Technology in Computer Science and Information Technology from AKGC College, India, and I like to play sports and do public speaking when I'm free. And also I do at times content writing. And this time I will be debuting in open source contributor as an open source contributor. And I do have a very keen interest in core networking and cybersecurity. Well, let's jump on to a situation where our packets are passed in for the features. And as you can see, I have tried to show that same thing over here, where I have depicted the features and the feature values. Now, these features are generally consisting of our 5 tuples and all their metadata. And that basically combines the stateless features and stateful features. And here the important focal point will be the stateful features, because these features actually creates a add-on value to the machine learning decision trees, because these have much better understanding about the packet or about the packets. And thus, for some examples over here are fin flag count, total forward packets. Basically, these are the features whose properties are defined not by a single packet, rather than an entire flow or across multiple packets. Well, as we're talking about the stateful features, there is a very intrinsic problem existing over here, which is its inefficient management in the machine learning framework. Now, what happens is recently there has been a lot of machine learning models implemented on a traffic, Now, as you can see over here, I have tried to depict a conventional decision tree, which is having 15 of nodes over here. And what I'm trying to convey over here is, in this table over here, that there is a stateful memory. Now, stateful memory is something in which we will have storing the number of features and number of flows with a very peculiar relation, where that if number of features increases, the number of flows has to decrease, and the vice versa too. It's a reason being the n into m result will always be constant, which turns out which is true again, because again the networking chip is having a very constrained amount of SRAM and TCAM present over it, and we can't really change those things. And we have to work with whatever the restricted stateful memory we do have. And what is the problem with this conventional decision tree over here is that in a conventional decision tree, before any inference occurs, the conventional decision tree requires to, first of all, do the feature collection of entire packets in the flow, which is actually not a very pretty solution. Reason being, because first of all, if you want to do feature collection of all the 2n packets, for example, over here, we have to take in consideration of all the packets plus their features. And considering the stateful memory is very limited, this creates a very big problem over a very contrasting problem over here. And to often tackle this problem, what we have also seen in the Leo and the NetBeacon research papers are, which has done the similar work over here, is they have kind of, rather than using all the features, they kind of have bottleneck to best k amount of features. So rather to implementing all the features of all the packets coming in a flow, they only play with the features which are probably creating the most differentiating factor in the inference. Now, although it's a very efficient move, but we are still not able to cover all the features, and thus this means the efficacy of the system will not be to its best. Although they have maintained the line rate, but to tackle the same issue of having the high efficacy of the inference while also maintaining the flow, while also having like a high amount of flow, we propose a solution called as split decision tree, also called as partition decision tree. Now it's a very beautiful idea, and also a very simple one, where we actually are implementing a very simple, if I have to say in a very simple form, it will be basically a sliding wheel algorithm working over here. So what we are doing here is we are actually dividing the entire decision tree into a small subtrees, and in all the subtrees we are assigning a small ID to it. For instance, here you can see there is SID 0, SID 1, SID 2, SID 3, SID 4, etc. Now, what's different from this from this previous decision tree, as we all saw? Now, the difference over here is, like, rather than first of all collecting all the features, then performing inference, what we are here doing is, first of all, we are taking, for instance, if I'm going through the, if my features pass into the SID 0 and pass into the F0, and let's say if they pass into F1, now what happens over here is, as the features first pass into SID 0, only the F0, F1, and F2 features are only loaded in the stateful memory, which means we are not storing all the features. Rather, we are only storing only the features which are present in that particular subtree. For instance, if we are working on SID 0, we will be having F0, F1, and F2 over here. Now I'm talking about just a flow 1. Now, for instance, if my control went from F1 and the inference coming from the F1 points me to SID 2, which will be done by the application of recirculation. But as I went, as for instance here, if my control goes from F1 to F4, during this process where one decision tree one subtree is is pointed to the another subtree, what happens is the old is existing feature, which is F0, F1, and F2 are replaced with the new features, which will be F4, F9, F10 in the instance. So what we are basically doing is, rather than installing all the features, we are only installing the features which are present in a particular subtree, and as we iteratively pass through it and come to the classification, we keep on iterating and replacing the same stateful cells in a memory. And by this, what happens is we are not flooding the stateful memory, which is a very important point. Now, just to explain this much better, I try to create a simulation over here. Yeah. So as you can see over here, there is there's a two windows over here. This window will be showing the simulation, and this window will be showing the basically the stateful memory. The simulation purpose is just to explain how the SRAM is affected in the conventional decision tree, where there is where we have to take all the feature as we have to do all the feature collection versus the split decision tree. Let's see. As you can see, the simulation occurs, there is a sudden flood of all the existing features. Now, this is not really a very ideal situation, because this can either cause a very long queue, or as I mentioned earlier, we just limit all the features to just the best case features, just not to flood the stateful memory. Now, this is not a really, it's not a really viable option. Now I want to show how it is different, which is how the split decision tree is trying to resolve this issue. Over here, okay, yep. Now this is the same simulation, which is for split decision tree. I have tried to implement the same. I have implemented the split decision tree over here. Now, as you can see, there are nodes, and each node are having their SIDs, which is nothing but subtree ID and identification. Now, what you can see observe over here is like, okay, let me start. It is starting, and as you can see over here is like, I have to pause for now just to explain this part, that as the features and the headers are passing inside the decision tree, only the features which are part of that particular subtree are only loaded over here, rather than storing all the features over here. And okay, how to back? Yep, yeah. Now let's see how it will work through. Yeah. So as you can see, for some reason, I'm not able to.
Sagar, I'll be short on time, so let's
All right.
get
All
to
right.
the others.
I will just move ahead. Yeah. So as you can see, the stateful memory never floods. Rather, it only takes in account of those memory which is always present in that particular subtree. Well, that was pretty much about it, about the simulation. Moving ahead, what are the challenges? As now it's quite understood that the challenge is the very strict switch resource limit, which is we have limited TCAM and SRAM. And also, as existing models have only the fixed top K features, we want to support almost all the features of the packet to have, again, the better efficacy. And now there are some more additional things which we want to do, is like convert these trained models into efficient deployable P4 match action logic, and also automating this entire pipeline. Now this entire pipeline looks like this. If I were to give a very skimmed view about it without wasting much of a time, we get an input of a data set, a target, which is our P4 Tofino, Intel Tofino, an objective being maintaining the efficacy while also maintaining the flow count does not decrease. And so this is a split compiler. It is actually performing all the Bayesian algorithm through hypermapper and providing us the optimal partition decision tree model. As this is our decision tree model which we have obtained from this compiler, what it does is it provides actually two outputs, a JSON file and a pickle file. And now we have another component which is basically a generator. This generator will be having two different kinds of generator. So through this JSON file, which is nothing but provides how the decision tree are actually partitioned. And through this particular file, we will be able to create a P4 generator. We will be able to compile all the pipelines of a P4 and create the P4 program. This P4 program will be compiled through P4C. This P4C will have the output. There will be multiple outputs, but considering over only the binary output and the P4 info file, we can use the P4 info file and use the runtime generator, which is nothing but the P4 runtime client. Now, what it does is, it is just basically an installer. Through the use of pickle file, it will be able to install all these rules into our P4 code. Now, here P4 runtime client will contact through gRPC the P4 runtime server, and again our target driver being the Intel Tofino chip. We are working over here mostly in Intel Tofino 1, and as you can see over here, it is Intel Tofino 1 over here. And since this target binary will be installed already, this P4 file will be running inside that Intel Tofino. Through this P4 runtime server, we will be having the installed all the match action unit rules, which will be implemented into Intel Tofino, and will get the classification, whether generally the packet is malign or benign. Well, coming over the deliverables, there are basically four deliverables, A, B, C, and D. A part has been kind of already finished by my mentors. It was basically, again, to use the hypermapper to actually provide the most optimized decision trees, and using the CIC flow meter to actually take the packet features and understanding the TCAM and SNAM entries. And right now I'm working in the P4 data plane action items, which is in progress, which is nothing but I'm understanding about the RMT architecture, and I'm trying to actually simulate the synthetic traffic on the P4 Studio, and trying to implement the same partition decision tree logic over here. Coming over to the C and D part, in the controller action items, in a very concise way, I would like to say it's like basically automatically generating the controller program using P4 and the context file. And about the automation and deployment, it is nothing but automated end-to-end testing using Moongen. What is Moongen? Moongen is nothing but very high performance traffic simulator, and using Ansible playbooks, which are nothing but it provides an environment to run scripted files and able to perform very complex codes and pipelines. That's pretty much about it. Coming over to the future scope, well, I feel it has a very huge future scope about this project, because it will be we can able to right now we're just working on Intel Tofino 1, but we have Intel Tofino 2, and we can work on many other chips. Also, we are now running not a dynamic subtree, but we can add in future scope. We can integrate in the production scale, especially in the DDoS detection and other flow classification, which I mentioned before, and also in a very different interpretable models like random forests in P4. And that's about it. I feel I took a little bit longer time, though I'm open for the Q&A session.
So any questions from the audience? Okay, so thanks, Sankar.
Yes, sir.
Yeah, also thanks to our speakers today. We are already past time, so I guess let's just conclude here. Thanks, everyone.